Hi, my name's Jeff Curry, and I've done a few presentations for different people at different levels, from the novice through to the intermediate and expert, on the application of artificial intelligence, machine learning, and deep learning in medical imaging, radiology, and nuclear medicine. So this presentation kind of pairs it back a little bit and starts to look at the very introductory principles around the application of deep learning in medical imaging. I've built the theme around Harry Potter, as you can see, and we're going to call it a Muggles Guide to Deep Learning Wizardry. Arthur C. Clarke is quoted as saying, "Any sufficiently advanced technology is indistinguishable from magic." And I've used that in a few different applications, including in deep learning. The idea that what we're doing is magical because we don't know what's going on behind the scenes. So that makes us think about what J.K. Rowling said when she said that we all have magic inside us. And it's kind of true, because what it means is that even though that when we're a beginner in artificial intelligence, we don't really understand the technology, so it all seems like magic, that we all have the capacity for that magic inside us. And so we just need to understand the beginning principles, so some of the terms and technology that I'm going to introduce today. And then in some cases, to advance that to be actually the magician themselves. So I'm not about to create a presentation that prescribes that you'll all become wizards of deep learning, but I certainly want to give you an oversight of how this works so you can better understand the world of magic in artificial intelligence. So this presentation will take a stepwise approach. I'm going to use the 7 books of the Harry Potter series to actually work through some different principles and applications of artificial intelligence, and in particular, deep learning. And so we're going to start with the Philosopher's Stone, book 1. So like the Philosopher's Stone, artificial intelligence is lauded for its astonishing powers, its capacity to save lives, and the potential to transform something that's ordinary into something that's more valuable. And so along the way, there's some criticism. So we have some Voldemorts and Death Eaters that are attributed as saying things or predicting that artificial intelligence would end the role of the radiologist or the careers of radiologists. More conservative approaches or perspectives predict that there'll be significant changes to the way medicine is practiced, and that's probably more realistic. It doesn't mean that people will be redundant. It just means we're going to change the way we do things. So the wizardry of artificial intelligence and its performance relates to deep learning, the algorithms that are associated with deep learning, and compared to the experienced physician or the radiologist. So one of the aspects of it is that there's been reported lower error rates for deep learning compared to the radiologist or nuclear medicine physician in interpretation. And this is a fourfold reality. So the first is that algorithms are looking at the problem differently, which could improve human training. So if the algorithm solves a problem by looking at it differently, then maybe humans can learn to look at the same problem in a different way. It's not always clear how the algorithm itself makes the prediction. So that's the magic box or black box. And that threatens the external validity of any algorithms that are developed. There's also a number of biases in artificial intelligence that are associated with only celebrating the successes, and we don't sort of recognize that there's a whole bunch of failures along the way. And of course, judgment and decision making relies on the cognitive capability of the radiologist or the nuclear medicine physician, which goes beyond artificial intelligence. And it overlooks the value of the art or intuition associated with being a physician or radiologist in that interpretive environment. So true wizardry requires a balance of crafting of the science and the art of the physician's world, creating a whole that's more powerful than the sum of its parts. The most common applications of deep learning in medical imaging have been for object detection, so for example, location of a lesion, object segmentation, so for example, lesion contouring, and object classification, so for example, malignant versus benign lesions. There are, however, many other applications of artificial intelligence in radiology and nuclear medicine, and you can see on the figure here that they include, without being limited to, a number of things, including triaging urgent cases for interpretation, so triaging normal versus abnormal anatomy, the degree and severity of disease, and importantly, identifying those urgent cases for priority reporting. Image enhancement and noise reduction can enhance the image quality and reduce radiation dose to the patient. Image reconstruction with direct transformation from a sinogram, for example. Attenuation correction can be done using pseudo CTs, and that obviously suits a SPECT-only system or a PET-only system without the CT dose, or PET MRI, for example. And that reduces the overall radiation dose to the patient and provides attenuation correction for PET MRI. There's multimodal image co-registration and feature extraction for things like SPECT-CT, PET-CT, PET MRI. And in the figure, you can see that there's a bit of a spectrum of artificial intelligence applications in nuclear medicine and radiology, with deep learning emerging outside of the red portion of the spectrum, so, sort of towards the middle. So the red end of the spectrum tends to be a little bit more of the machine learning side of things, so business analytics, risk assessment, quality assurance. And then we start to see the emergence of our deep learning applications, triaging, segmentation, and quantitation I've mentioned, the extraction of radiomic features, reporting, in particular the secondary reporter process, calculation and dosimetry, and then starting to delve into things like deep radiomics and decision making. So there's insight to be gained from unpacking a simple convolutional neural network algorithm. And so consider a convolutional neural network algorithm designed for detecting pathology on a chest x-ray, and specifically for identifying suspected pathology to triage for prioritized reporting. While such a convolutional neural network is not designed for diagnosis itself, its cited performance metrics are generally against a radiologist's reporting rather than against its ability to triage. So that's kind of interesting. In actual fact, the validated performance may not be assessed against current triage protocols, which makes the whole exercise a little futile. And thus the actual performance in practice cannot be fully understood. Furthermore, it's not always clear how the convolutional neural network has arrived at the outcome or prediction. So unpacking that magic box or black box of a convolutional neural network, I guess gives you an insight into how the neural network triages that chest x-ray. So it may reveal an illusion rather than any tangible insights. For example, an x-ray being performed mobile or supine suggests that the patient actually has a greater degree of infirmity and has an increased likelihood that the patient has any pathology. The presence of central lines, ECG leads, or a pacemaker also provide clues to the convolutional neural network that the patient has increased probability of lung pathology. So none of these factors cause the lung pathology, but collectively they increase the probability that the chest x-ray will be abnormal. So it creates a bit of a conundrum, and I'm going to call it Dumbledore's conundrum, because I'm referring to Professor Elliot Siegel as our Dumbledore. So deep learning predicts with 75% certainty on an x-ray that a patient has a central line present, but we don't know for sure if it found a central line on the x-ray or identified a disease patient that should have that central line. So that's kind of interesting. And so you can see the images here show a chest x-ray, and these numbers, this is part of a heat map, and it's color coded, so the yellow through to purple. The yellow areas actually contribute more significantly to the determination of pathology. And so you can actually see that areas where you've got leads, areas outside of the actual lung fields themselves are actually contributing quite significantly to making a prediction of whether the patient has pneumonia or not. And so this is really important because a radiologist would be more concerned with the lung fields, whereas in this particular case, the deep learning algorithm seems to be more concerned with what's going on outside the lung fields in making that prediction. So when we talk about artificial intelligence, we sort of need the sorting hat to actually decide where everything fits. So some things will fit more broadly into the artificial intelligence domain, and this is not to scale. The artificial intelligence domain is an enormous area of activity, from robots through to some of the algorithms that we use. Within artificial intelligence, there's a smaller section that refers to machine learning and artificial neural networks. A subsection of that is representative learning, and then a subsection of those is our convolutional neural networks and deep learning. So let's step into book 2, The Chamber of Secrets. The emergence of deep learning in medical imaging has heralded the greatest disruptive technology since the early days of Roentgen, Becquerel and Curie. With disruption comes the risk of opening the chamber of secrets in deep learning. And this may be the detriment of Muggles yet to master the wizardry of deep learning. In medical imaging, the artificial neural network really is the backbone of deep learning. An artificial neural network is an analysis algorithm composed of layers of connected nodes. The inputs may be patient data, for example, in an Excel spreadsheet, could be radiomic features that we've extracted through quantitation of our data. And if we're actually using the images themselves as inputs, well, then we'll actually use a convolutional process to connect to a convolutional neural network. Radiomics are useful features that are extracted from the radiological data. And that includes nuclear medicine data and involves delineating the lesion of interest, so regions of interest or some sort of AI segmentation, to extract the actual features or information themselves. But radiomics are more than just image quantitation and involves the extraction and analysis of higher dimensional data to improve decision making. So radiomics captures the spatial parameters associated with radiological imaging and the molecular parameters in nuclear medicine. First order radiomics relates to shape and spatial features of signal intensity like volume, sphericity, data density, acoustic signal, and obviously count density. Then we have second order radiomics which relate to the intensity or mathematical associations between pixels and voxels. And these things are like histograms for mean intensity or maximum intensity. Then we have third order radiomics which relate to the textural features. These are things like gradient and heterogeneity of features that are produced with the application of kernels or filters, or wavelet transform and harmonization are really good examples. Amongst that, we can have multi-parametric radiomic features that are extracted from co-registered images of PET-CT, for example, so you've got multi-modalities, or from a single modality like MRI, where you're actually looking at multiple MRI sequences. With such richness of data coming from imaging alone, any given patient could have hundreds of features that could be inputted into neural networks. So the discussion on the last slide is really summarized in this image. The image shows the radiomic feature extraction pipeline, highlighting a variety of radiomic features that can be extracted for data analysis. So in this particular case, we've got PET-CT, MRI being inputs. From that data, we're able to segment particular regions and bits of information. So we go through a 2D and 3D segmentation process. That segmentation could be manually or handcrafted regions. It could be automated computer-generated regions, or it could be artificial intelligence-driven segmentation. From that segmentation, you can develop a number of features. So the feature extraction could be first-order shape-based radiomic features. They could be those intensity-based second order features, or we could be looking at those third order features where we actually apply filters and kernels to create textural kind of features for extraction. And all of those features are inputted into some form of data analysis, and that data analysis could be decision tree analysis, or in our case, is that we might want to input those features into a neural network for machine learning analysis. So as an example, let's say that we had a database of 500 Hogwarts students over a period of hundreds of years. And we could randomly partition those into, say, 300, 100, and 100 cases. So that would be a 60-20-20 split of your data or your students into training, validation, and testing data sets. So when we actually start to ask the sorting hat to learn how to correctly identify abstract features of those students that would help them decide which house those students should be in. So the inference phrase would be then the current application of each student being sorted into those different houses. So you can imagine that in those early phases when it was training, that it might actually see a feature and think that that is consistent with Gryffindor and sort the student into that domain, and that could be wrong. That could be shown to be wrong over a period of time, and so the sorting hat will learn from that and make its adjusted calculations in order to better predict those abstract features that would define which house a student should be defined as. And of course, when we actually start to think about the magic that's associated with deep learning, we can actually start to think, well, this quote from Severus Snape, as there is little foolish wand waving here, many of you will hardly believe that there is magic at all. I don't expect you to really understand the beauty of the softly simmering cauldron with its shimmering fumes, the delicate powder of liquids that creep through human veins, bewitching the mind and ensnaring the senses. And that really is deep learning. There's not a lot of wand waving, but there is a whole bunch of magic that simmers away in that cauldron. So an artificial neural network is comprised of nodes configured into a number of layers, and that number of layers creates the depth. So deep learning utilizes an artificial neural network, but has many layers to create that complexity. Each node in an artificial neural network is connected to each node in the subsequent layer, and that would make it a fully connected neural network, and provides a weighted input, which means each node receives a weighted input from each node in the preceding layer, as you can see in the figure. So the goal of an artificial neural network is to train to maximize the accuracy against some sort of grounded truth. So we know what the answer is, and so we have inputs that come in and we adjust the weightings on the nodes to try to have the output match the grounded truth. So an artificial neural network's output is compared to some form of grounded truth or gold standard, and we just adjust those weightings through an optimization algorithm where we have parameter increments. So you can see that down in this aspect of the diagram at the bottom, where we recycle a number of iterations through, adjust those weightings on the individual node, and see if we can actually result in a better outcome, which is a lower error. So with each iteration or epoch, the artificial neural network converges on a more accurate solution or answer. Obviously richer data, so larger data sets with more diverse and inclusive populations, improve the accuracy of the training. A second partition of the data set is then used to validate and refine the architecture. And you can see that process on the right-hand side of the image. And so essentially what you're actually doing is optimizing the architecture complexity, so the number of nodes and the number of layers, but also which input features should be included. So you can see that we've gone from having 1 through to n features as an input with 19 nodes in 4 layers to having just 2 features inputted into a much smaller number of layers, 7 nodes and 2 layers. And resulting in a less complex neural network, and this decreases overfitting. And then we can use a third partition of the data set to process through the artificial neural network, comparing it to a grounded truth to actually then measure its accuracy. So our final architecture, we can then test its accuracy against that third data set to predict how well it's going to perform in the inference phase. So as an example, the data set of 500 Hogwarts students from hundreds of years ago being randomly partitioned into the 300, 100 and 100 cases, giving us 60% for training, 20% for validation and 20% for testing. So that's a 60-20-20 split, and sometimes it'll be a 50-25-25 split to allow the sorting hat to correctly identify those abstract features. So moving on to book 3, The Prisoner of Azkaban. Developments in computing technology have sort of liberated artificial intelligence from its Azkaban, but the value and capability need time to produce strong evidence of efficacy, build trust, and I guess drive away any of the dementors that are floating around. So the artificial neural network architecture includes a scaling layer as inputs, so it formats the inputs into appropriate numbers. a number of hidden perception layers, which gives the depth, multiple nodes or perceptrons per hidden layer, which gives it its complexity, and an unscaling layer. And that unscaling layer then leads to a probabilistic layer, which provides your outcome. So each perceptron has weighted inputs combined with a bias and shaped by an activation function to produce a single net input for each node. And so while data is the input for an artificial neural network, a convolutional neural network will have images as an input tensor, which is converted to data through a convolution process. And we'll show that shortly. So here we can actually see a convolutional neural network example where the convolution process downsamples the input tensor, so the input tensor being the image, and applies multiple kernels to highlight potential trends or features in the data. So via an activation function, feature maps are produced and further downsampled via pooling stages. The pooled feature maps will undergo one or more additional convolution steps, more kernels, another activation function, and additional pooling stages for downsampling before it's finally flattened into a single dimension for input into the neural network. So in this particular image, you can see up the top there that, and I've sort of done it numerically at the bottom, we'll go through that in a second, representation of the convolution using a 3x3 kernel. The weighted sum of the kernel for the 3x3 input tensor creates a single representative value for the feature map. So here you can actually see that within this 3x3 array, that if we apply this kernel, then we actually produce a single feature. So this is the weighting of the different pixels. And so we end up with an accumulation of 9 plus 8 plus 7 plus 7 plus 12 using this particular kernel would give a weighting of 43. So those 9 pixels would be replaced by a single pixel with a value of 43. And then you would do that for multiple groups of 3 pixels. So we produce multiple feature maps by changing this particular kernel. So that's represented here where the actual kernel itself will have different weightings and different representations to produce different feature maps. So instead of it being 43, it might be represented by a different number and a different pattern. So then we actually go through the pooling stage where we have a 2x2 pooling. And if we call this max pooling, it's called max pooling because for each 2x2 array, that we actually replace that 2x2 array by the maximum pixel value. So in this case of this 2x2 array, the maximum pixel is 43, so this becomes 43. In this particular zone, the maximum pixel in this 2x2 array is 32, so you end up with a value of 32. Down here it is 31, so it becomes 31, and in here it becomes 35. So that is actually the pooling stage, and that pooling will occur for each of those feature maps. It could then undergo additional convolutional processes, which create additional depth, and each of those would be associated with additional pooling steps. But then when we actually want to flatten it into a single layer for input into the neural network, we simply turn it on its side and stack it. So 43, 32, 35, 31, and that becomes a single dimension for input into the neural network. So radiomic features can be extracted from the input tensor in the shallow layers of a convolutional neural network that are similar to those of non-AI augmented features. So there's different types of radiomic features. So even though the radiomic feature might come from a convolutional neural network, it may come from those shallow layers and be very similar in nature to the standard radiomic features like SUV that might be extracted from using quantitative parameters in a standard processing method. But we can actually have more abstract features that can be extracted from input tensors in the deeper layers of the convolutional neural network. And these are actually referred to as fourth order radiomic features, and they're referred to as deep radiomics. So remember in previous slides, I talked about first, second, and third order radiomics plus the multiparametric radiomics. Well, the deep layers of a convolutional neural network that produced really abstract kind of radiomic features. That's the fourth order radiomics or deep radiomics. And unlike radiomic features that are extracted using AI segmentation, including from convolutional neural networks in the shallow layers, these deep radiomics are extracted from the entire input tensor without the need for segmentation itself. So this is sort of a Patronus level combination of convolutional neural networks and deep learning radiomics that casts a powerful spell over the precision medicine landscape. So during convolution, a number of kernels are applied, and each convolution produces depth within the overall process, as you can see in the figure below. So max pooling downsamples and additional convolution steps add further depth. After the last convolution and pooling step, we have to flatten the data so it can actually enter the neural network. So a simple convolutional neural network might resemble the layers that you can see on this screen. Obviously, it's more complex than is depicted, but it gives you a general impression that we start with our input tensor, which could be 224 by 224 pixels with a depth of 3, and that is converted into or entered into the convolution process, the convolution layers and activation function, to produce the same spatial domain, but with 64 kernels to create a depth of 64. This could then actually undergo a downsampling process, so max pooling, where we actually reduce our spatial dimensions to 112 by 112, but we actually deepen our data by adding another 128 kernels. Further downsampling down to a 56 by 56 spatial array, but 256 depth with those kernels. Further downsampling and increased depth. Further downsampling, now we're down to a 14 by 14 array. Eventually we're down to a 7 by 7 and then ultimately a 1 by 1 array, because it needs to be one dimensional to go into the fully connected neural network, but with 4096 in terms of its depth. It will go through the neural network and then you'll have some sort of softmax output on the other side. So a simple way to describe the convolution and pooling process is to consider a simple character image on a matrix. So the images that you can see on the screen. So like Sirius Black, there's more to understand than what is apparent to the observer. So let's look at these two examples. We have convolution, pooling, and flattening processes for the image from a matrix. It should be noted that there are typically, 32 to 512 kernels for each convolution step, and numerous convolution steps, in a complex neural network, convolutional neural network. But here we've actually simplified to allow us to assist the understanding of the process itself. And so you can see a potted plant, and you can see the matrix that's represented. And if we apply this kernel, where the black might represent a numerical value of 1, white might represent a numerical value of 0. Now the stride means how many pixels we skip before we apply it again. So a stride of 3 means that when we apply this pixel, we're going to apply it for the first 3 by 3 array, and then we're going to move directly to the next 3 by 3 array. So there's no actual overlap. If the stride was 1, then we'd apply the first 3 by 3 array to the first 9 pixels, and then we'd only just move 1 pixel to the right, and then it would be applied to the next group of 9 pixels. And that would be in both dimensions. So when it actually stepped down to the next layer, then a stride of 3 means it would go from being here to being here, and a stride of 1 would go from being here to then being these 9. So we apply our kernel, and so when we apply that kernel to this data, we end up with a feature map that looks like this, and it bears no semblance to this image itself. So when you look at it, you can see why these weightings have produced this image, but if you saw this feature map on its own, you would not be guessing that this is what the image looked like. So then we actually go through that 2 by 2 max pooling, and you end up with something like this. and then we flatten that into a one-dimensional layer, and you end up with that as the input into the neural network. And remembering there could be, hundreds of these kernels that are applied, which would then make the flattened version a much larger dimension. So let's look at an even simpler image as an input tensor of this cross. So if we apply the same kernel, then you end up with a feature map that looks like this. When that's pooled, but in a 2x2 max pooling, it looks like this, and then it's flattened, and that would be the input into the neural network. So let's step into the goblet of fire. So each year the RSNA has a version of the Tri-Wizard Cup, which is the annual artificial intelligence challenge that attracts teams from across the world, casting their entries into the goblet of fire. The true value of deep learning wizardry comes when we test it against authentic clinical challenges. So in visual or image-based deep learning, the convolutional neural network is designed for and tasked with 4 basic operations: classification and object recognition, classification and localization, object detection, and instance segmentation. So the range of applications of deep learning in nuclear medicine can be generally divided into clinical applications and physics applications. Key physics and instrumentation applications include, without necessarily being limited to, attenuation, scatter and motion correction, co-registration and reconstruction, low-dose imaging and noise reduction, and radiation dosimetry. Pseudo-CT attenuation maps for standalone PET or SPECT and in PET MRI, and for dose reduction protocols have emerged as a really important application of deep learning, and is depicted here in this image, with a high degree of accuracy being reported across a number of groups that are doing research in this domain. So here you can actually see an example where you might have sinograms from a PET image that are inputted into a neural network. And so this would actually go through a convolutional process first. And from those images that are inputted, those sinogram images, that you would actually predict a pseudo CT. So what do you think the CT would look like, or what does the neural network think the CT will look like based on the PET sinogram? But in this data, when we train the neural network, we actually train it by actually comparing the predicted pseudo CT to the actual real CT. And what it can actually do is then adjust the weightings to improve its prediction, so that ultimately you've trained it to be able to predict with fairly close accuracy the pseudo CT that closely resembles the actual CT based on the PET sinogram. So then we can actually co-register the pseudo CT to the PET data, and we can use that for iterative reconstruction and co-registration and attenuation correction. Dose reduction strategies are also important, and in nuclear medicine, I guess they're part of image quality, but also diagnostic integrity when we try to reduce our radiation doses to patients. So a number of approaches have been reported in the literature, including an encoder-decoder architecture, which you can see on the screen here, with doses in the range of as low as 0.5 to 1% of the standard dose. So you can imagine that reducing the actual dose that's administered to the patient to 1% of what we currently administer, and being able to generate image quality without actually losing any image quality over the standard dose rate. It's kind of a little bit unheard of, but it's really important around dose reduction strategies. Similar approaches can be used for noise reduction. So some of our nuclear medicine images can be noisy, both in SPECT and PET, and we can actually use it for noise reduction to maintain image quality. And so what you end up with is a encoder decoder kind of scenario where you have your input image, which could be a low dose CT, it could be a low dose PET scan, low dose SPECT scan, or it could be an image that has a bit of noise in it. And you could actually go through a number of convolution and normalization activation steps with max pooling in each step. go through a graph neural network module, and then come back with a decoder system, which actually is then the upsampling. So this is our downsampling side, and then we upsample back into an image. So rather than having an output that is a prediction of disease, our output then becomes a newly formed image. So we downsample our image in terms of the data of the image, and then we upsample the image and image data to produce a denoised image. And that denoised image could be associated with either an original or noisy image, or, as I said before, a low dose study. So here's another encoder decoder setup without the skip steps. So PET sinogram in, we go through an encoder. So this is obviously a U-net. You can see the shape of it is a U-net. So we have an encoder half and then a decoder half, where we actually go through our normal convolution and downsampling steps, and then we actually go through our upsampling and image formation step. So this is an example that you would use for direct reconstruction of your PET image or your slices from the sinogram. So instead of using your iterative reconstruction or your filter back projection, we're actually using a algorithm, an encoder decoder algorithm, to reconstruct your slices directly from the sinogram itself. And that same process or similar process using a U-net encoder decoder system with a graph neural network could also be used to predict what images will look like at different stages down the track after therapy. So when we actually have serial lutetium therapy images, then we could actually predict based on, as a starting point, our gallium-68 PSMA scan. We could use that to predict what our dosimetry will be, and then we can correct it by comparing it to the actual lutetium gamma camera images that are done at 4 hours, 24 hours, 96 hours. We can then actually use that to train the encoder decoder system to better predict what the dosimetry will be over based on the original gallium-68 PSMA image. So this is going to be really important in adjusting therapeutic doses to patients to optimize outcomes for disease treatment and minimize collateral damage, in particular to kidneys. A large portion of the current literature relates to deep learning approaches to automated disease detection, classification, triage of, and segmentation, which I've already mentioned, and also assisting in diagnosis. So there's a diverse array of applications in nuclear medicine. We don't need to go through them all, but predicting major cardiac events in myocardial perfusion SPECT, providing superiority over expert readers and quantitative software that we're all familiar with. There's applications that look at deep learning approaches to detection of Alzheimer's disease on FDG PET. There's deep learning approaches to identification of high-risk patients that are likely to benefit from chemotherapy. That study was done in nasopharyngeal carcinoma. There's a nice study that looked at renal segmentation using convolutional neural networks in lutetium PSMA studies to estimate radiation dosimetry. There's convolutional neural network based auto segmentation to determine metastatic deposits on bone SPECT, which improves staging and determining of the tumor burden. Deep learning applications in FDG PET CT can predict treatment outcomes in patients with oral squamous cell carcinoma with near 90% accuracy. And detection of seizure foci in FDG PET brain, regardless of whether it's ictal or interictal status, using a convolutional neural network has been particularly useful in pediatric patients. And these are just a very small snapshot of what is capable of being done in nuclear medicine. And so what we're actually finding is that, more and more our nuclear medicine departments are conjuring those Patronus spells that can drive away some of those dementors that are associated with challenges that we've encountered in nuclear medicine diagnosis. And I really love this. This comes from 2019, published in the Journal of Nuclear Medicine, because I think that we can get really bogged down with what is artificial intelligence, what is deep learning, and how we interpret it. And this is how I think the future of nuclear medicine quantitation is going to go. So when we actually look at, and these are two different patients left and right, but when we actually look at the polar maps that we can see on the screen, this is already artificial intelligence. The generation of these polar maps is already artificial intelligence. So when we start to think about artificial intelligence starting to infiltrate nuclear medicine, artificial intelligence has been part of nuclear medicine for more than a couple of decades. And so it's not new to nuclear medicine. The language is new, and perhaps the application of neural networks is new, but artificial intelligence itself is not. So it kind of makes sense that the way that we integrate our deep learning architectures into our clinical realm is using something very simple. And so here you can actually see that we don't see the convolutional neural network. We don't see the complexity of what's going on behind the screen. We're not actually trying to predict or understand what the magic box is doing. What we're doing is producing an output that is not only easy to interpret, but it also integrates with the way that we actually currently present data. So a deep learning algorithm that predicts the probability of coronary artery disease in each of the territories on the polar map. And so here you can see 62% probability of coronary artery disease in the left anterior descending territory. And in patient 2, where there's triple vessel disease, then the deep learning algorithm predicts that there's 84% probability that there's disease in the left circumflex. So I think that's the way we're going to go in the future. So that brings us to the Order of the Phoenix. So while neither artificial intelligence nor ethical practice are new to medical imaging, nuclear medicine, or radiology, recent developments and applications in deep learning sort of demand a new order of leaders to guide ethical and social implications of artificial intelligence implementation. Artificial intelligence has the potential to improve workflow, reduce costs, increase accuracy, drive equity, and empower research. But it can also do the opposite of all of those things and have quite a negative impact. So in nuclear medicine and radiology, implementation of artificial intelligence through the AI pipeline has been occurring in parallel to navigating the ethical and social implications of that artificial intelligence pipeline. So those committed to the order face a number of challenges related to ethical considerations. And that includes the data used and also the algorithms that are applied. And the role of the algorithms in healthcare, inequity and bias are really important aspects of that order. So while the foundations of ethical implementation of artificial intelligence in healthcare are consistent with those of medical practice generally, things like autonomy, benevolence, justice, and respect of knowledge, deep learning demands specific attention to data, privacy, and confidentiality. It's important to consider the social impact of artificial intelligence augmented decision making on the community. It is possible that withdrawing AI augmentation, so it might be a patient choice or it might be inequitable access, so it's possible that withdrawing that AI augmentation might result in less optimal outcomes. There are also a number of guidelines developed in radiology addressing ethical use of artificial intelligence, and more recently in nuclear medicine. So you can look at those in the reference list if you want to understand more information. So if there's underrepresentation of any particular subgroup in an algorithm for either the training or validation, so minority groups, vulnerable groups, pathology subgroups or subtypes, then you introduce bias and error that can drive greater health inequity. And of course, inequity and bias associated with artificial intelligence can result from a lack of diversity in the teams of data scientists and the clinicians that develop the artificial intelligence tools. And when artificial intelligence algorithms are trained on homogeneous data, we can also introduce inequity and bias. So both implicit bias, which is unintentional prejudice, and explicit bias, which is those conscious attributes that produce bias, can be deeply ingrained in deep learning algorithms. Of particular importance in healthcare is institutional bias because it's historically weaved into the culture and it may not be obvious, but it's learned by the deep learning training and it drives further social asymmetry. And I just wanted to draw your attention to this image. Is that the image on the right are obviously Voldemort. Sorry, the images on the left are obviously Voldemort and his Death Eaters, and the images on the right are part of the Order of the Phoenix, who were supporting Harry and Dumbledore. And one of the things to note is that there is a degree of diversity in the Order of the Phoenix, and there is a distinct lack of diversity in the Death Eaters. So global, national or local disparity in opportunity and also access to healthcare among communities creates a gap that could be bridged by artificial intelligence, but it could also be widened. Particular care needs to be taken to ensure marginalised communities are represented in training data and also in problem selection. It's important that they have access to the artificial intelligence tools and that they are not exploited. And the exploitation can come from data privacy and ownership issues. We should also keep in mind that the technology demands of typical deep learning algorithms prohibit direct benefit to communities without advanced internet and computing access, which is 41% of the global population. That's correct. 41% of the global population do not actually have access to the internet and computing services that would require even the basic machine learning, let alone deep learning. And of course, limited indirect benefit to those living without electricity. So there's still 16% of the global community that live without electricity. So nonetheless, digital and energy poverty need not prohibit problem selection for artificial intelligence algorithms and the development of those solutions. And we can actually target the communities that could benefit from artificial intelligence algorithms and developments. So it's our choices that show what we truly are far more than our abilities. So some of those choices are about how we choose to use artificial intelligence. Do we use artificial intelligence to further drive the capability afforded to first world health systems? Or do we harness the capability of artificial intelligence to try to actually better understand and manage health issues in developing health economies without necessarily having the infrastructure on the ground in those developing economies to run things like complex deep learning algorithms for image interpretation? So the typical negative cycle of inequity associated with the artificial intelligence pipeline in general and in healthcare is displayed in the blue aspect of this diagram. So we need to start with the pipeline. It runs from problem selection to data collection, outcome definition, algorithm development, and then obviously implementation and evaluation. And the negative cycle starts with inequity and discrimination, a lack of diversity and inclusivity in the data. The reinforcement of institutional bias and power imbalance. And so then we develop algorithms that learn and reinforce those biases, and as a result, we create a much bigger gap. And so what our job is to do, and certainly those people that would take up the order to develop social equity and ethical practice in artificial intelligence, is to actually use problem solving to target injustice. And by targeting injustice, you ensure that data collection is both diverse and inclusive. And by doing that, you actually start to overcome some of those biases and imbalances, and are directly addressed by decoding those institutional biases and encoding neutrality in the algorithms. And that's really important because then we can actually have external validity and start to address some of those inequities. Artificial intelligence algorithms are largely developed by higher income countries, and developing or undeveloped economies currently lack the resources to exploit the capabilities of artificial intelligence. Artificial intelligence augmented healthcare in the wrong hands can reduce outcomes and produce outcomes that are counter to the first do no harm mantra of medicine and non-malevolence. So the role of the order is critical for ethical, legal, and social justice in the application of artificial intelligence. Moving along to the Half-Blood Prince. In the first iteration of artificial intelligence in medicine, algorithm development was largely driven by teams of pure-blood computer and coding wizards. The real art of artificial intelligence in nuclear medicine and in radiology was not realised until our Muggle medicos became part of the development teams. Today, we reap rewards of half-bloods and mudbloods that drive artificial intelligence development through a lens of imaging expertise rather than coding expertise. Nonetheless, there remains an eagerness amongst our Muggle fraternity to craft an AI footprint. And that's what this presentation is all about, to actually try to bridge the gap and empower those Muggles amongst us to be able to be part of the team, at least, understand the language and contribute to the development of an artificial intelligence footprint in your departments. Large-scale development projects are probably beyond the average department from both an expertise and a resource perspective. There are, however, quite a few projects and opportunities to improve practice in low resource projects. I guess the first step is to develop capacity for developing your own code. Now, not everyone's going to be capable of that, but if you can develop your own code for a neural network, it avoids the costs of purchasing those software packages. And there's software packages that are both intuitive and fairly comprehensive that allow a novice to use a graphical user interface to develop and run neural networks without actually the capacity for doing coding themselves. And so if you have the funding to do that, it's a really easy way into the market. In either case, whether you're doing the coding or whether you're using the software interfaces, the key is planning, understanding, and astute problem selection. Like architecture, coding and algorithm development should be driven by the maximum form follows function. So before stepping into this space, you need to think about, what you actually need. Familiarize yourself with the landscape and the language. There will be challenges and risks that are not obvious to the naive or novice eye. The first steps really are to consider the following. What is the problem or question? How can artificial intelligence address it? What artificial intelligence technologies do you need? And what artificial technologies do you have available? What data is available? What impact will artificial intelligence solution have? Because if it doesn't actually produce a solution that's usable, then you're wasting your time. There's an enormous volume of potential deep learning applications in nuclear medicine and radiology, but it's critical to identify a problem and an appropriate tool to solve it, recognizing that many problems don't actually need artificial intelligence. In fact, is that you might actually find that even when they do, that machine learning solves the problem without the need for deep learning. So the image on the screen there is a schematic representation of the relationships between hardware, code, the frameworks, the architectures, the libraries, the data sets, and then of course the deep learning solution itself. So the deep learning landscape is defined by the two orange zones, and the deep learning ecosystem by the purple and yellow zones. There will be challenges and risks that are not obvious to the naive eye that might need a Loomis charm to cast some light on both the problem and potential solutions. The quick way to get an artificial intelligence footprint in your department might actually be to recruit yourself a house elf. Obviously, that allows you to actually import the expertise to do the artificial intelligence deep learning coding. So that brings us to the Deathly Hallows. The term singularity relates to development of superhuman intelligence that will end the human era. The principle is not dissimilar to the doomsday thinking cited with respect to radiologists, or indeed the ambitions of Voldemort. Singularity relates to the point where artificial intelligence learning and advancement kind of steps beyond the control of humans and becomes irreversible. The Deathly Hallows is where the combination of advances are greater than the sum of the individual developments. A counter view to the demise of humanity at the hands of superintelligent AI is that in the right hands, artificial intelligence developments could lead to significantly advanced human life expectancy. So let's think about the Deathly Hallows. Artificial intelligence does not understand pragmatics or higher order logic, And so for that, it requires quantum-based logic. So in computing, data is stored in bit form or binary. So yes or no, 0 or 1, dead or alive, for example. The qubit is a quantum bit of information where superposition allows data to be yes and no at the same time, 0 and 1, or indeed both dead and alive simultaneously. Qubits are entangled with other qubits, even when separated by large distances. So, like the resurrection stone in the Deathly Hallows, superposition can be fractured by outside interference in a process called decoherence, where the qubit reverts back to being a bit. Quantum computers wield extraordinary power capable of completing calculations within seconds that would have taken conventional computers, even current supercomputers, thousands of years. Quantum computing could solve problems that were previously thought unsolvable. So like the Elder Wand, the power of quantum computing is unrivaled. Blockchain is a technology that's developed for cryptocurrency that is a distributed digital ledger, keeping a record of transactions decentralized at multiple sites. A change in data at one point in the chain produces changes in each point down the chain. So it's very difficult to sort of hide indiscretions. Coupled with artificial intelligence, blockchain could have a role in data security and privacy. So like the cloak of invisibility, ensuring privacy and security by securing all of the data through data sharing. So quantum computing uses qubit-based quantum logic, which combined with blockchain level data security could produce quantum neural networks, authentic intelligence or synthetic intelligence, and singularity. So they would be the Deathly Hallows. Artificial intelligence and deep learning have an important place in the future of nuclear medicine and radiology. Seamless assimilation with exploitation of the power of deep learning to improve outcomes while minimizing ethical, legal, social challenges demands fairly broad understanding of the wizardry of deep learning across the profession. And of course, making sure you have the right tools for the task is crucial. Here, in this presentation, the minimum level understanding is presented to allow Muggles to look behind the curtain at advanced technology that drives deep learning. But keep in mind, there's always a new adventure around the corner, and who knows where the deep learning journey will take us. Lots more information can be found in these articles. And I guess that there's an opportunity for questions and discussion. And I've just popped up a few quotes just for people to think about. From Alice in Wonderland, you know what the issue is with the world. Everyone wants some magical solution to their problems, but everyone refuses to believe in magic. And that's kind of true with the artificial intelligence landscape at the moment. As Einstein said, we can't solve our problems with the same thinking we used when we created them. And that sort of really means that there's an opportunity for artificial intelligence, machine learning, and deep learning to solve those problems that have been created elsewhere. Artificial intelligence is a golden age and solving problems that were once in the realm of sci-fi, and I think we've seen that. Automation is Voldemort, the terrifying force nobody is willing to name. And that's a little bit of truth that everyone wants those magical solutions that I mentioned from Alice in Wonderland, but at the same time, people dare not use the words artificial intelligence and deep learning because we fear artificial intelligence or we fear automation and the implication of automation because we probably don't understand it. If you only have a hammer, you tend to see every problem as a nail. And so artificial intelligence provides so many tools to problem solve that it's actually allowing us to unravel the mysteries of many problems previously thought unsolvable. Predicting the future isn't magic, it's artificial intelligence. And of course, the last one, artificial intelligence and magical thinking, is really what this presentation was about. And I hope that perhaps putting it into I guess the context of Harry Potter and the Harry Potter series perhaps made it a little bit more interesting, or at least allowed you to stay engaged for a little bit longer, so you picked up a bit more information.